Okay, so I hope you are seeing the 4 memory hierarchy questions.
Yes, ma'am.
Okay, all right. So the first part we have already discussed, right? Second part is basically how do you find a block if it is in the cache? So how do you determine whether it's a cache hit or not, which we have also discussed, right? Then which block should be replaced on MS? I'm not covering these also because these are all done in your OS. So P4 random LRU. And the set associative cache example clearly shows how nicely LRU is used for the two-way set associative cache, right? So if you have a four-way set associative cache, then basically you need 4 bits. Okay. What they do, they check the bit corresponding to the block. And if it is set, then they say, okay, it's been recently used, and so on. So they basically look for a bit which is 0, which says that this hasn't been used recently, and replace that. If all of them are 1, then randomly one of them is chosen. Everything is reset. You know how LRU approximation works, I hope. So that's essentially how it works here. If you do not know, now please, this is basically what is happening here. I assume you have learned something in COA. I assume you learned something in operating systems. I assume you have seen the videos that I have put up. And therefore, I move fast on those matters. Now, if there is some problem with any of them, you are not sure, or you need more explanation, please ask. Otherwise, I'll be going at my usual breakneck speed. And the thing is that, it is, in fact, choosing to do asynchronous is in some sense more challenging for you. It's not difficult for us so much, I would say. Even though it's confusing to us, it's not difficult for us as teachers. Because we have done a lot of hard work finding good videos, right? After that, our job is simple. We assume you have seen it, and we'll only answer questions on those videos from you. If we have to teach, we have to go through a lot of stuff, right? All of that stuff we have to go through. So it'll take time. And if you don't come prepared for the class, like I wrote in a mail to Bansi, you will not be able to follow the class very well. It'll only make the situation bad. So if there is something you don't understand, please do stop and ask. The second thing I also wanted to say was, if people are having major problems, please send email, or whatever, and set up appointments like you do in the office hours in the university. It will be a private Zoom meeting for you to make you catch up with whatever issues you're having understanding. Okay. Please do feel free to set up such meetings and, make sure you understand the subject.
Okay.
So I'm assuming, like I said, FEO, random LRU and all are known to you. You want me to explain something, I'll explain. If somebody needs explanation, please let me.
Ma'am, could you go through
Yes.
LRU once?
Okay. In LRU, okay, let's take the two-way set associative example that the video talks about. So basically, they have the two-way set associative. So he has LRU bits. Okay, so you have way 0 and way 1 here, right? This is way 0 and this is way 1. Okay, and you have here LRU bits. Okay, so here he maintains either 0 or 1. Okay. In fact, you have 2 bits, let's say. Initially, you will have 0, 0. What does that tell you? That both way 0 and are both not used, right? If you have blocks like this, or I mean, you have sets like this. So for each of the sets, you have basically initially 0, 0, because nothing has been used yet. And now, supposing that you bring a block into this particular way, right? So you, let's say, some hit here. Okay. When there is a hit here, you go and modify this value. You modify that value and make it 1. Saying that you have basically accessed way 0 in that particular set. Okay. Now, if way 1 is accessed, then accordingly you basically modify way 1's bit also. So now you have both are 1. So there is a hit at time t0, let us say here, right? T0, and there is a hit at time t1, right? So we have hits in both the ways, and therefore the bits are both set to 1, whereas the blocks in the other sets are not set to 0. Now, supposing you are trying to get some block which falls into set 1 itself, right? And both the bits are set to 1. Therefore, it means that both have been accessed recently. Okay. Then you randomly choose one of the 2 ways to replace with the new block. Supposing you choose to replace way 1, then what will you do? You will basically, at this point, set both bits to 0. Okay. Set both bits to 0 and replace this block with some block, right? And this will basically also be you can think of it as erasure, because we have reset the bits to 0. There is a hit at time t2, right? There is a hit at time t2, and now you set the bit corresponding to way 1 to 1. Okay, so you get your bits to be 1 and 0. Now, supposing you need to bring some other block into this set, okay, then what do you do? You see the LRU bits. It says 1 and 0, which means that way 0 was least recently used. So you will replace way 0 with a new block at this point of time. Don't know if I made myself clear.
I understood partially. I think
Yeah,
it's
what did you not understand?
no, like initially, like also like I couldn't remember much from COA, so I thought about like keeping the memory hierarchy aside so that I could actually get down to listening into it properly. But I still remembered that LRU was, I think, the hardest way because I remembered direct addressing and sister associative quite well. So I just wanted to like have you clarify LRU
Basically,
properly.
LRU is also covered in OS, right?
Yes, ma'am.
Page
Yes, ma'am.
replacement, you do
Yes, ma'am.
LRU. So it's the same thing in here, block replacement also. So let me just repeat once again. When you start off, so you have one bit for every block that corresponds to, for every block in the set,
Yes,
right?
ma'am.
If you have two-way set associative, then you have two bits in the LRU. Okay. Initially, both the bits will be zero because neither of them is accessed yet.
Yes.
Every time you access a particular block, you set the bit corresponding to that block to one.
Yes, ma'am.
Okay. So now, supposing you need to bring in a block into that set, a new block into that set. What do? You go and check the LRU bits. In our case, we have two-way set associative. So if you look at our set one, basically here is our set one here, right?
Yes, ma'am.
So in set one, we find that the LRU bits are 1 and 0, which means that wave 1
Has
is
been accessed.
has been used recently and wave 0 has not been used recently.
Yes, ma'am.
Okay. So you need to bring a block into that. Since the bits are 1 and 0, you will replace way 0 since
Yes,
that
ma'am.
is least recently used as per the LRU bits. On the other hand, if you had both 0, you can replace any of them randomly, one of
Yes,
the
ma'am.
two. Okay. If both are 1 also, you can replace either of them. But in this case, what will you do? You will first reset both bits to 0, right? If both bits are 1, first you will reset both bits to 0, randomly select one of the two blocks to replace, and whichever block you have replaced, the bit corresponding to that block you will set to 1 because you will be accessing it now.
Yes, ma'am.
So it goes like that. That's the algorithm that is repeated.
Okay, ma'am. I understand it now.
Okay, any questions?
No, ma'am. I understood it quite.
Ma'am,
Thank
so
you,
in
ma'am.
case of FIFO and random, like in case of FIFO, will there be any bit storing something like that?
Yeah, I guess you have to have there also, right? FIFO is much more difficult in some sense here because they're not really, um, unless you maintain some sort of a pointer between the blocks, then you can easily determine FIFO, right? Or they may always, yeah, you have to do that way only. Because you can't go by the numbers.
Yes, ma'am.
Initially, you can try numbers like way 0, way 1, way 2, way 3. They're in that order, we can think. They're filled in that order. But replacement also will happen in that order. So at some point, 1 or 2 will be at the head of the queue. So how do you know which is at the head of the queue at that point of time?
Yes, we need
You have
to.
to maintain either the head of the queue information because that is all you need to replace. So if you have, so the number of bits you will have to maintain in that case will be equal to the, log number of blocks per set to the base 2.
Yes.
Right, and then you can maintain the number of the block which is at the head of the queue, and whenever you need to replace, you replace that, because that becomes the free for block. Random is easy, it's the easiest, right? So pick up one of the blocks and just replace them. LRU and FIFO will require additional bits to be stored to determine which block to be replaced.
I don't think that also like works, because at some point, even like if you are storing the head pointer, we need to know which is the uh, next one which has to go out. It that might not.
Order will be the same. I mean, order will not be an issue. No, it'll always go 0, 1, 2, 3.
Yes, ma'am.
You'll first fill 0, then 1, then 2, then 3. So you'll replace 0 first, then 1, then 2, then 3. So
Yes, ma'am. Yes,
it doesn't change. The order doesn't change.
yes.
Any other questions on the first 3 questions? Because then I'll be moving to the right strategy. Otherwise. Did you do this in your COE?
Yes, ma'am.
Okay. So can you explain right through? I wrote update all levels of memory hierarchy, which may not necessarily be true, but we'll discuss that. What does it mean? What does write through mean?
Like whenever page is modified by a process, it is updated in cache and in main memory as well.
Okay.
And
So,
write back whenever page is modified, it's only modified in the cache by setting a dirty bit to 1. So
okay.
whenever the page is has to be replaced in the main memory, it's updated.
Okay. Whenever you have to replace it in the cache, only then you update the main memory, right? So, but I said update all levels of memory hierarchy, because if you have multiple caches, do you update all the way through or do you not? I did say all levels because, like you said, I was looking at level 1 and main memory as the 2 levels at this point, in which case, you are updating your cache and main memory. But supposing you have a layer 1, level 1, level 2 cache, and then main memory. Should you write through from level 1 to level 2 to main memory, or stop at level 2? That's a question. If you have 3 levels of caches, which is very common nowadays, level 1, 2, 3, and main memory, how many levels do you write through?
Maybe
And
only in level 1. Maybe only level 1 is required, madam, because every process will first access through level 1.
no, but write through means you write not only to the cache but to the lower levels also.
Yes, ma'am, but writing in all the levels will take much time.
Yeah, so where do you stop? If you have level 1, level 2 main memory, you are saying I'll write to level 2. But if you have level 2, level 3 and main memory, what? You'll write up to level 3 or you will write only up to level 2?
I guess only up to level 2.
Okay. So these are, the questions which will come up, not immediately, but when we go to the final chapter, right? The problem of cache coherence will come up. What do we mean by that? I have one value in level 1 cache, I have some other value in level 2 cache, or I have some other value in the level 1 cache of the core. Now, if different cores are accessing the same data and they're having different values in their level 1 caches for the same data, how do you handle that problem, right? So many complex questions come up when you are having different levels of caches and you don't keep the data coherent or the same across all levels of memory hierarchy. So it is a difficult question, and we will learn how do you handle cache coherence in the final chapter. But for now, we will assume, we'll sort of ignore that question, right? So right through at this point, we haven't yet talked about multi-level caches. So we write to level 1 cache and main memory, okay? Write back only when the block is replaced in the cache. At that point of time, we write that block back to the main memory. So it's called write back. And these two are options when you have a write hit, right? So the block you are trying to write to is available in the cache. When it is available in the cache, you can choose to do either write through or write back. Okay, that's basically the thing. Now remember that we said whereas the time to access the cache is 1 clock cycle, time to access the main memory is 200 clock cycles. So if you do write through, you're going to have many clock cycles because you have to write to the main memory, and that will stall the processor. Okay. So one solution to that is using what is called as a write buffer. So what is this? This is a very small, a few words of very fast memory. Okay. So you write to the cache and you write to the write buffer, and later in the background, the write through will happen from write buffer to the main memory while the processor continues to execute, right, without stalling. You are going to take data from the write buffer and write it to the main memory. So by doing this, we can reduce or avoid memory stalls. Any questions on what is write buffer?
No.
Now, when there is a write miss, so you are trying to write to a block and this block is not available in the cache. What do? One possibility is you allocate, allocate meaning that either you bring that block from main memory into cache or replace some block in the cache with that block from the main memory. There is a miss, right? So you're fetching that particular block from main memory into the cache. This is write allocate. After you fetch that block from the main memory into the cache, then you do the operation of write into the cache. So when you do the write operation into the cache, again, it's like a write hit at this point of time. So you can either use write through or write back. Okay. But on the other hand, another option is when you are trying to write to a block, you don't find it in the cache, you don't bother to bring it into the cache, you simply write it only to the main memory. Okay. Now, what's the advantage of doing this? If you compare the advantages and disadvantages of write allocate and write no allocate, can you tell me what are the advantages and disadvantages?
Ma'am, in write allocate, as we are updating only higher level of hierarchy, the updation will be fast and the updation will be fast.
Yeah, but you have to fetch it, however. Yeah.
In then
So, what is the advantage of fetching it?
Like the cache will be with the modified data, it's with the fresh data.
Okay. Supposing you are using write through as your policy, right? You're not using write back, you're going to use write through. So, does it matter that you bring it into the cache?
no, then
No, ma'am.
because
I think either Zoom is eating up some words or whoever is speaking is swallowing part of the word.
No, ma'am, it's not required.
So, I mean, the thing is, if you do bring the block into the cache, what advantage do we gain?
temporal locality
Yeah,
might increase the cost.
spatial locality is likely. Supposing the assumption is that if you write one word or one byte into a block, the next write also happens to the same block. If that spatial locality, does exist, then yes, bringing it into the block makes cache makes sense, right? So you do allocate, you bring that block from the main memory into the cache. But if you are implementing write through, then you are anyway going to actually write not just to the cache, but also to the main memory. Then, fetching it into the cache may or may not fetch you a significant improvement. It may lead to improvement in the case of write buffer being, but if no write buffer is used, then there is no improvement in the cache. Let me again reiterate what I'm saying. Supposing you are using write through, okay, what does it mean? Even if there is that block in the cache, you will update the block in the cache as well as update the block in memory. Okay. If you are not using a write buffer and the block is not in the cache, then simply writing it to main memory is not a problem at all. Because anyway, into the cache, you have to write also. Okay. So this particular scheme where you write no allocate with write through or write down, and it's the special case. Right? It's the simplest to implement, but write series of write, then you will, basically be able to take advantage of that if you have a write allocate and write back. What is happening in a write back? Multiple writes to the block happen and one write to the memory happens. So you will reduce the number of times you access the main memory also. So the bandwidth to the main memory requirement also comes down compared to write through. Okay, there are two parts to the memory access. One is the latency, which we talked about, which is miss penalty. The other is the bandwidth. Bandwidth is how many, words of data can you exchange with the main memory in a certain amount of time, right? So that bandwidth, is also limited for main memory. So using it less often will make it more efficient. Okay, that is the thing. Okay, so there are another 5 minutes left, I believe. Any questions on this? Write through, write back, write allocate, write no allocate. Somebody is not clear.
Ma'am,
Yeah.
can't reading and parallel, or like while the
Reading and
cache is
writing.
writing into the while the cache is writing to the higher level, can't the CPU just execute the other things as it doesn't, like, does that affect the, how does that affect the CPU in a way? Like, how does it affect the CPU if cache actually wrote the, like, when you write something to a
Yeah,
CPU,
it
how does it
depends on how many ports your cache has for access. If it has separate read and write ports, then maybe it can do in parallel.
so then it wouldn't matter to CPU if it's taking time for the cache to write to the main memory.
Yeah, but if you're trying to access the same block,
Okay.
right, that would be difficult, isn't it?
Like if you are
If
trying
you
to
if
access the
both
same
your
block
write
multiple
and
rows.
read are accessing the same block, then what do you do? Because the tag matches and all,
Yeah.
right, have to happen on the same block, isn't it?
But when cache is writing to the main memory, that time
Mhm.
lag wouldn't be seen by the CPU, right? Like after the
Why
CPU
not?
writes.
Because the cache will not actually be operational in that time period for
Oh,
reading also.
okay, okay. So while it's writing, cache won't be available for
While it is
CPU.
actually being accessed to write.
Okay.
So unless you have, like I said, if you have two ports, right, read port, write port sort of a thing, which may help, but even there it may not always help because see this multiplexers which you need to access multiple tags at the same time and compare the tags, because when you every time you try to read data, you have to index into the set and then compare the tags of all the blocks in that set. Yes?
Yes, ma'am.
If we are talking about set associative.
Yeah.
Then, the multiplexer has to be, if it's already in use, set to a particular block for the write, then it cannot be set for the read to some other block, right?
Yeah. Yes, ma'am.
So you'll have to replicate hardware, and that's what I mean, multiple ports and all. It makes it more costly as well as more power consumption. And possibly, that solved much better, much faster, with less power and all by using something like the write buffer.
Yeah. Got
So I think, we are almost, I think the meeting will be cut very shortly, maybe in another minute or so. So, yeah,
1 minute.
yeah. So let me just talk about this one equation and then we'll get cut and we'll come back. Sorry, I haven't given you a break today, but hopefully because it was interactive, it's not so bad. So instead of, as a, one, typically people think that a good way of measuring the cache performance is the hit rate or the miss rate. Okay. Either way, it's the same, right? One is the complement of the other. But that's not such a good measure. Better to use average memory access time, which is basically hit time plus miss rate into miss penalty. Okay. I have a problem that we will be discussing after we come back from the break. I thought that's probably one problem, at least let me go through, so that in fact I don't usually go through problems, but maybe I thought it's worthwhile to talk once and see if people are comfortable. Okay, so this is the average memory access time.